Greetings to all. In last video we have discussed about linear time and linear time invariant system. It is one of the type of discrete time system, and with that continuation we are going to discuss about the another type of discrete time system, that is stable or unstable system. And for checking the stability of a system, now we are going to consider two cases. Very first one is bounded input and bounded output case, and the second one is impulse system, that is impulse in the sense h of t. And now in this unit we are going to focus mainly on the very first case, that is Bibo system, and we will be discussing about the second case on the second unit. And so for getting the stability, the output should not be equal to 0 as well as infinity. It means if for a bounded input, the output also should be of a bounded value, and if you are going to give the value of input as 0, and for that output should not be equal to 0. And if you are going to give an input as infinity, and for that the output may be infinity or may not be infinity. So likewise we have to check the stability of a system. And so on the whole we have to keep in mind is the value of the output should not be equal to 0 as well as infinity. And we are having several types of elementary signals, that is input, and the basic bounded input, in the sense now we are going to focus mainly on the DC signal as a bounded input. It is constant throughout the entire time period, starting from 0 till infinity. It will be constant value. And the second thing is unit step response. It is also a bounded input. And third one is sinusoidal and cosine. All these signals we can consider as a bounded input. So with the help of these four bounded signal, we are going to check the stability of a discrete time system. And before getting into the numerical problems, we'll look into the elementary signals available, and hope you might have studied all this type of signals with mathematical expressions in a control system. And the very first one is unit step function, mathematical as u of t. The value of a step function is always 1 for a time period starting from 0 to till infinity, and for less than 0 the value of unit step function is 0. The unit refers to the value 1. Since we are calling this as a unit step function, the step function value always will be equal to 1, and we can say the same expression in terms of discrete as u of n. For continuous it is u of t, and for discrete it is u of n. The same thing, but in terms of we are going to replace t as n. And this is the diagrammatic representation for unit step function. We are having the value magnitude of step function as 1 starting from 0 till infinity, and the value of step function u of t or u of n will be 0 for less than the time period or the discrete index less than 0. The second function is ramp function, and we can relate this ramp function in terms of unit step function as t times of u of t. And or else we can say that u of t is nothing but the differentiation of ramp function, and this is the graphical representation for ramp function. And third one is impulse function or delta function, and the value of impulse we can relate with the step function as it is del of t is nothing but differentiation of u of t, and it is the graphical representation along with the mathematical function. If the del of n will be equal to 1 only at time t equal to 0 or n equal to 0, otherwise the value will be 0. So now we'll see the numerical solutions to understand the stable and unstable condition of a system. And now the problem is y of t is equal to sin t into x of t. And now we are checking only for the very first case, that is Bibo condition. So now we have to consider any one of the bounded signal. So we are having 4 bounded signal. One is DC, second one is unit step function, third one sine wave, fourth one is cosine wave. Now we will consider the input as a DC signal, that is bounded input. DC signal is constant, just like a unit step function. It is having a constant value starting from 0 till infinity. Likewise, the DC signal is going to function. So DC signal, the magnitude is 2 here, because the first one is unit step, so that the value is keep on maintaining at 1. But whereas here we are going to consider as a DC signal with a magnitude of 2. Okay, so the x of t is 2 here, so we can replace this equation as y of t equal to 2 into sin t, that is bounded output. Because why we are telling this as a bounded output, since we can say that we all know that the value of sin theta varies from -1 to +1 at maximum. Likewise, cos theta also is having its minimum value is -1 and maximum value is +1. But whereas tan theta is having value of infinity. Right, so we can say that sin and cos theta as a bounded value, but whereas tan theta and all is not a bounded value, because its value reaches to a infinity. Okay, and now we can say we are having equation as 2 sin t, and now we are telling this as a bounded input. Since the value of sin theta varies from -1 to +1, we are telling this value, this system as a stable system. It means we are getting for finite input, we are getting a finite output. Okay, and we'll check with another bounded input. We can take instead of DC, we can check with unit step function. We can take x of t as u of t. So now the equation will become u of t into sin t, and we know the value of sin t varies from -1 to +1. It is always a bounded one. Now we have to check with the u of t, and if you are going to substitute the value of t as 0, what will happen? The u of t will become 1, and again it will give a bounded value, because now we are substituting the value of t as 0, and at this time the output should not be equal to 0. This is the condition for checking stability for Bibo system, right? So we are substituting the value of t as 0 here as well as here, and for y of 0 the value will become 2 sin 0. And whereas for this case the value of t is 0, at the time the y of 0 will be equal to u of 0 into sin 0, and we know that sin, whatever may be the value of sin, the maximum value will be 1, the minimum value will be -1. So need not to bother about this sin value, and we have to look on to the next term, that is u of t, and the value of t is now 0, so u of 0 is also 1. So at the time of t equal to 0, we are not having 0 output, we are having some bounded value. So we can say this system as a stable system, because we are getting bounded output for bounded input. The second numerical problem is y of t is equal to t times of x of t. At time t equal to 0, what will happen? We will be getting y of 0 as equal to 0 into x of t. Whatever may be the value of x of t here, anyhow we are going to substitute, or we are going to replace x of t by means of bounded input, either as a DC signal or unit step signal, or even sin or cos theta. Whatever may be the value of x of t here, we are having t in proportionate to x of t. So if you are going to substitute the value of t as 0, what will happen? The entire equation will become 0. But our condition for stability is the value of output should not equal to 0 as well as infinity. But here at time t equal to 0, we are getting the value as 0. Now we'll check for time period at infinity. At infinity, what will happen? Again it will move on to infinity. So in both the cases it is reaching, it is not within the bounded value. So we can say from this condition that this system is not a stable system. We are having 4 questions to check the stability of a system, and we can take these questions